express 721 as a product of its prime factors. So how do we approach? So we have 721 and we are straight away going to prime factorize it. So we can do it like simply 7 into 103. And is 103 a prime number? Is 103 a prime number? So that will be the question. So you have to build the practice so that we can quickly have a feeling that whether a number is prime or not. Otherwise you can actually try different factors. In this case 103 is a prime number, so 721 can be prime factorized as 7 into 103. Okay, determine the prime factorization of 13912. So we have 13912. So 13912, we know it's an even number, so let's start with 2. 2 into 6956 you will get, then you continuously do, you'll get 2 into 3478. You can further do 2 into 1739. So we have 1739. Now the confusion will be, how do we factorize 1739? One way is that we go by the numbers 2, 3, 5, 7, 11 like that. That is one way to do it, but that may take a lot of time to eventually get to the correct factor. One thing that we can see is that the last digit is 9. Okay, so how can we get 9? So 9 can come, means 3 can be a factor, or we can have 7 as a factor. And if you try 3 and 7, both 3 and 7 will not factorize 1739. So we can continue to do, you can actually look for prime numbers like 13, try 17. There is no point in checking 19. So how do we get this 1739? Okay, so 1739, what we are looking, we are seeing two numbers should be multiplied to get 1739. Okay, and we have the last digit as 9. So the last digits of A and B, right, it has to be either 3 or it has to be the 7. So some numbers with the last digit 3 into the some number with the last digit 3. So some number with the last digit 3 into some number with the last digit 3. So the last digit 9 can be only obtained if we have some numbers like, okay, and this has to end with 3 and this has to end with 3. Okay, then when we multiply these two numbers we will get 9. Okay, there is one more possibility, it could be two numbers with the last digit coming as 7, then also we can get 1739. So now you have to actually try some numbers to get it, and when you actually try it out you will get the answer as 37 into 47, and 37 and about 47 are prime numbers, so we finish our prime factorization. So the point is that once we know, okay, basically 3 and 7 is not going to factorize this, then it is better to look for prime numbers which is ending with 3 and 7 and try to see which number can factorize it. So this is one question which starts very seemingly simple, but then you end up with some number and you can actually spend a lot of time, and you can also build tension in solving this problem, like why I'm not able to factorize it. You can even be thinking that, okay, is 1739 a prime number or not? So when you build more practice, you will have the confidence of facing these scenarios, and also you will also have a fair idea about what are the prime numbers. So next time when you see a problem, you immediately know numbers like 37, 47 are prime numbers because it comes by practice. Now we go to the next problem, that is explain why 3 into 5 into 7 plus 7 is a composite number. So what is a composite number? A composite number is a natural number and it is greater than 1. So it has more than 2 factors. Okay, So in other words, it can be divided evenly by the numbers other than just 1 in itself. So let's say what is a composite number. For example, 9 is a composite number. Why? Because 9 has factors as 1, 3 and 9. So it has not just two factors which is 1 and 9, but there is one more factor 3 here. So it has more than two factors, which means 9 is a composite number. So in the given problem we have 3 into 5 into 7 plus 7. Now how do we check whether this is a composite number or not? If it can be written as a number which is having more than two factors, that means it is a composite number. Okay, so this we can rewrite it as 3 into 5 into 1. Okay, this I put it in bracket plus 1, and all together is multiplied by 7. Okay, so this 7 will come here and this 7 will come here, and then we will get the same number. Okay, now what have we seen? So whatever this number is, we have first factor here, we have second factor here, obviously we have 1, and whatever this number is, that is going to be another factor. So what it shows is that this is a composite number, and we can show that it is a composite number by writing it in this form as a multiplication of two different integers. For some integer m, every even integer is of the form. We have been given 4 options. So one is m, second option is m plus 1, third option is 2m, and fourth option is 2m plus 1. To solve this, it is better to go by one and see whether which one will satisfy the correct answer. Okay, the first we have m. Now can we say that for every integer m, every even integer will be of the form as m? I think quickly we can know that it is not. If m is an odd number, then simply m cannot represent every even integer, right? So we can quickly understand that option 1 is not the correct option. Let us look at the second option. Okay, the first case is that if m is an odd integer, then m plus 1 will become an even number. That means option B can represent every even integer, but that is only the case when m is an odd number. What if m is an even number? If by chance m is an even number, then m plus 1, that is option B, will become an odd number, and it cannot represent every even integer. So option B is also a false option. Let us look at the third option. So option 3 we have 2m. Okay, now if m, let it be an odd number or let it be an even number, irrespective of the case, we know if we take any integer and you multiply it by 2, you will actually get an even number. So option C will always represent an even number, and option C could be the correct answer. Okay, now you don't actually have to check option D or the fourth option, that is 2m plus 1, but since we are learning by solving problems, it is good to analyze the option D and see what we can learn from it. Okay, so option 4, let m be an odd number or m be an even number. When you actually try to compute 2m plus 1, you will see that let it be any number, it will always represent an odd number. Okay, if you have some doubt convincing yourself, let m be 6. Okay, so it is an even number. Now 2m plus 1, it will be 2 into 6 plus 1, and what will be the answer? It will be 13. It is a odd number. And let's take m equal to 7, which is an even number. Let us calculate 2m plus 1, and what will come? 2 into 7 plus 1, and it will come to be 15. Okay, again an odd number. So what you can see here, when we do this 2m, okay, which is our option C, you will always get an even number, whatever be the value of m. So 2m will always result in an even number, and 2m plus 1 will always result in a odd number. So option third is the correct option in this problem. This is the correct option. For some integer q, every odd integer is of the form. We have four options: q, q plus 1, 2q and 2q plus 1. Okay, so this time I will not go through all the four options in detail. It will be repetition. In the previous question, we have already analyzed all the four options and how these numbers behave. And now you will know that option D, okay, that is 2q plus 1 is the correct answer. Because why? First case, let's see q is even. We have seen that 2q plus 1 will always be an odd number. We have just seen this behavior in the previous question. Now the second case, q is not number, then again 2q plus 1 will still result in an odd number. So option 4 is the correct answer. So if you still have some doubt, you go to the previous question and clearly go through the way I have explained in the options, and then try to solve it, and then try to solve this question. If you still have some doubt, you can write it in the comment section. I will try to explain it later. Check whether 6 power n can end with the digit 0 for any natural number n. Okay, so how do we solve this? We have the number 6 power n, and that we can rewrite it as 2 into 3 whole power n, okay, which is same as 2 power n into 3 power n. Now can this value, whatever be the value of 6 power n, will it end with the digit 0 for any natural number n? That's a question. Okay, so if any number 6 power n for any natural number n, and if it were to end with the digit 0, then what we can understand, it should be divisible by 5. Okay, so that's the thing that we have to check. Okay, now what happens when we factorize 6 power n? We saw the factorization coming to as 2 power n and 3 power n. When we factorize, we see that the prime factorization will only contain 2 and 3, and 5 is not here. That means we cannot divide this number with 5, or in other words, there is no natural number n for which 6 power n ends with the digit 0. Okay, we move to the next question, that is, if the HCF of 65 and 117 is expressible in the form of 65m minus 117, then the value of m is. We can start this problem by first finding the HCF of both the numbers, starting with 117. So 117, we can factorize it as 3 into 39, and 39 we can further factorize it as 3 into 13. And now that 13 is a prime number, we can stop the factorization. So 117 is equal to, we have 3 into 13, or 3 square into 13. Similarly, the second number 65 we can factorize it as 5 into 13. Therefore 65 is equal to 5 into 13. So together HCF of 65 and 117, we can write the common factor, and that is only 13, and the lowest power is again 1. Thus 13 is the HCF of 65 and 117. Now it's given that given 13 is expressible in the form 65m minus 117, so we just have to equate 65m minus 17 to 13. Let us do that. 13 is equal to 65m minus 117, or 65m equal to 113 implies m is 2. So the answer is m equal to 2. The largest number which divides 70 and 125, leaving remainders 5 and 8 respectively is. To solve this problem, it is good to first represent both 70 and 125 with its divisor, quotient and remainder. That is, 70 we can write it as 70 is equal to some integer b multiplied by the quotient q plus the remainder, which here is 5. Similarly, 125 we can write it as 125 is equal to some integer c multiplied by the quotient q along with the remainder 8. We can represent any integer in this form, right? We will now rewrite the same equations. The first equation we can rewrite it as, if I take 5 to this side, and in the second equation I take 8 this side. The first equation becomes 65 is equal to BQ. The second equation becomes 117 is equal to CQ. Now we need not worry about what is the value of B and what is the value of C. The point here is that we have considered Q to be the highest factor of 70 and 125, and Q is also the highest factor of 65 and 117. So we have to find the highest common factor of 65 and 117 to get the value of Q. And once we get the value of Q, we will have the answer for the given question. Thus, the HCF of 65 and 117 is 13. We have just calculated the HCF for the same numbers in the previous problem, so I am not rewriting it. Thus 13 is the answer for the given question also. Thus 13 is the largest number that will divide 70 and 175, and it will leave the remainder 5 and 8 respectively. So any other similar problem that you can get, you can represent the same way and continue to do. We have to first represent the numbers in this form, and then we can transform it into this form, and then we have to find the HCF of these numbers. If two positive integers a and b are written as a equal to x cube y square and b is equal to xy cube, x and y are prime numbers, then the HCF of AB is. So it is a very simple problem. We are already supplied with the prime factorized form of a and b. Let us write it. So a is equal to x cube y square and b is equal to x y cube, and it is given that x and y are prime numbers. Therefore HCF of a and b all we have to do is we have to first write the common factors, which in this case are both x and y. So x here, y here, and the smallest power of x is 1 and smallest power of y is 2, or simply x y square. The answer is xy square, or option B. Can the number 15 power n being any rational number, end with the digit 0, give reason? So first of all, for any rational number n, 15 power n, we can rewrite it as 3 into 5 whole power n, or 3 power n into 5 power n. Now we have seen similar questions previously. In the textbook there is a problem considering 4 power n, and previously I have discussed a problem with 6 power n. Both were asking the same question, that is, will it end with the digit 0? So when we considered 4 power n and 6 power n, what we were looking is that whether 5 is a factor in the prime factorization of the number. And when we observed that 5 is not available in the prime factorization of those numbers, we understood that there can be no number which will end with the digit 4, 4 power n and 6 power n. In this problem, we can straightaway see that 5 is already a factor to this problem. Does it mean that for any rational number n, will 15 power n end with the digit 0? Actually, the correct way to look at this kind of problem is that to have a number which ends with 0, we need that the number to be divisible by both 2 and 5. In the previous problem with 4 power n and 6 power n, we already had 2 as a factor, but we didn't had 5. In this particular problem, considering 15 power n, we have 5 as a factor available, but we do not have 2. Once more, in this problem, 15 power n is divisible by 5, that is correct, but 15 power divisible by 2, that is not possible. Thus, the overall answer is no. 15 power n cannot end in a number ending with 0. The least number that is divisible by all the numbers from 1 to 10, both inclusive, is, the options are A 10, B 100, C 504 and D 2520. How do we solve this problem? What we have to do is we have to find the LCM of 1, 2, 3 all the way up to 10. We will now prime factorize all the numbers starting from 1 to 10. For 1, we have 1 as the only factor. For 2, we have 2 equal to 2. And for 3, we have 3 equal to 3. For 4, we can write it as 2 into 2 or 2 square. 5 is same as 5. For 6, I can write it as 2 into 3. For 7, it is simply 7. For 8, it will be 2 into 2 into 2, or simply 2 cube. For 9, it is going to be 3 into 3 or 3 square. And for 10, the prime factorization will become 2 into 5. So what will be the LCM? To calculate the LCM, we have to list down all the factors available. So those are 2 into 3 into 5 into 7. We have to also use the highest power of each factors. So that is going to be 2 cube, 3 square. For 5 and 7, it is simply 1 as the highest factor. So let us calculate. It will come to be 8 into 9 into 5 into 7, or the final answer is 2520. Therefore, option D is the correct answer. 2520 is the LCM of all these numbers. Find HCF and LCM of 65 and 112. For 65, we have done even in previous problem. It is simply 5 into 13. For 112, I can simply see 2 is a common factor, so I can write it as 2 into 56, and for 56 it is 2 into 28, and for 28 it is 2 into 14, and further it is 2 into 7. So let us write it together. 65 is simply 5 into 13, and for 112 it will become 2 power 4 into 7. Now the question is, what is the HCF and LCM of 65 and 112? So for HCF, we have to find the HCF of 65 and 112. And for that, we have to write the common factors of 65 and 112. But do we have any common factor? We can see that there are no common factors between 65 and 112. In other words, 65 and 112 together form a coprime. So therefore, HCF of 65 and 112 is simply 1. We will now also calculate what is the LCM of both these numbers. So LCM of 65 and 112, we have to list down all the common factors. We have to list down all the factors. So that is 2, and then 5, and then 7, and then 13. Now let us write the highest power of each factors. So for 2 it is 2 power, and for rest of them it is simply 1, and you just have to multiply all these numbers. I'll leave it as an exercise for all of you. Anyway, I will do it, and that will come to be 7280. Since we know that 65 and 112 form a coprime, we need not do this individual multiplications. We can directly multiply 65 and 112. Let us check that. 65 into 112 will give you 7280, same as here. So whenever we have two numbers which are coprime, to find the LCM of it, we just have to multiply it. There is no need to further write one more step of writing this individual factors and the highest power. We need not spend time on it. We can directly multiply the two numbers and get the answer. This is only in the case when the two numbers are coprime. Thus, LCM of coprimes is their direct multiplication.